In this video, we're going to talk about an introduction to vectors. A vector is a quantity that requires both magnitude and direction for a complete description. Examples of vectors are weight, velocity, and friction. On the other hand, a scalar is a magnitude that can be completely specified by just one number. Examples of scalars include age, volume, area, speed, mass, and temperature. A vector can be represented by a directed line segment. The magnitude of the vector is indicated by the length of the line segment, and the direction of the vector is indicated by an arrowhead on the end of the line segment. Now, as mentioned earlier, speed is a scalar quantity. We can describe the speed of an airplane as 200 kilometers per hour. Velocity, however, is a vector quantity. We can refer to the velocity of one airplane as 400 kilometers per hour in a southwesterly direction, and that would be represented by the vector A in the diagram down below. And then we can also talk about another airplane as having a velocity of 100 kilometers an hour in a northerly direction. So notice that the magnitude of this vector is about 1/4 the magnitude of that vector. It's helpful to make our diagrams in such a way that it looks that way as well. We can indicate movement in a direction from one location to another using vectors. So for example, the vector AB is a line segment running from point A to point B with its tail at A and its head at B. And its actual size or magnitude would be denoted by what we call the magnitude of AB. When you write AB with what look like absolute value bars, we call it the magnitude of AB. And it's represented by the length of the line segment. Now, the magnitude of a vector will always be non-negative. In fact, it'll always be positive unless we're talking about the zero vector. The direction of the arrow represents the direction of the airplane, and its length represents the speed. Now, two vectors, AB and CD, are equal if and only if AB and CD are parallel to each other and the direction from A to B is the same as the direction from C to D. And if the magnitude of AB equals the magnitude of CD. There are also opposite vectors. Two vectors AB and CD are opposite if and only if AB and CD are parallel to each other and the direction from A to B is the opposite of the direction from C to D. Another way of putting that would be direction from A to B is the same as the direction from D to C. In other words, opposite of C to D. That, and also to be opposite vectors, point 2, the magnitude of AB would equal the magnitude of CD. Let's talk about vector addition. You can determine the sum A plus B by putting the tail of B on the tip of A and then drawing a vector straight from the tail of A to the tip of B. And the resulting vector would be called the resultant. And this method is sometimes called the tip to tail method. And it looks like this. So in other words, we want to know what the vector A plus B will look like. So what we can do is we can draw a vector A, and then from the tip of vector A, draw a vector B. And then what we'll have done is given ourselves an opportunity to go straight from the beginning to the end. We call that resulting vector A plus B. And a way of thinking about the sum of two vectors is as follows. If you walk from point A to point B, and then walk from point B to point C, the net result is as if you walk from A directly to C. And so therefore we say AB plus BC equals AC. Now, suppose we have an airplane traveling with a component velocity of 500 kilometers per hour north. When it encounters a wind blowing with a velocity of 100 kilometers per hour east, what's the resultant velocity? So what we'll do, we'll draw the component vector. Now, a word that we're using here is component. One of the components of the resultant vector will be what the airplane is traveling at. And then another one will be, sorry, it looks a little curved there. Another one will be the wind. And what's going to happen is we'll be able to add those two together and come up with this resulting vector. Well, what we want to do is figure out the length of that vector and its direction. So to figure out the length, because it's a 90-degree angle, it's a pretty straightforward question. It's just a Pythagorean theorem opportunity. The magnitude of r quantity squared will be 500 squared plus 100 squared. So the magnitude of r will be roughly 509.9. But that doesn't tell us velocity. We want to know velocity. That tells us speed, but the velocity will require direction. So what we do is go to the resultant vector, which is this one right here, and go to its tail. So go to the bottom, the part without the arrow, and figure out an angle that is related to that corner of our polygon, usually a triangle. And so we're going to do that, and we're going to have actually an opportunity to use SOHCAHTOA. Tan theta will equal 100 over 500, and theta will be roughly equal to 11.3 degrees. Now, we're going to be able to therefore say that the resultant vector, the magnitude of this vector, will be roughly 509.9, and we'll be able to say that the direction was north, but then 11.3 degrees east, approximately. Now, when we're told the angle between two vectors, it's always the angle between those vectors if they're drawn tail to tail. But note, however, that when we add two vectors, the angle that we use for our sine law or cos law calculations will often not be the value used when given the angle between two vectors. You'll see what I mean in this next question. Let's imagine that we're given two unit vectors, A and B, with an angle of 30 degrees between them. Well, first question you might ask is, what does this mean, unit vector? It means a vector with a magnitude of 1. Well, we've got a couple of vectors, magnitude of 1, and there's an angle between them of 30 degrees. So we can draw A and B, and we can draw ourselves a helpful diagram like you see down below. Now, we'd like to know the magnitude and direction of 2A plus B. So we begin by drawing the description given in the first part of the first sentence. Simply draw A and B, draw them tail to tail, put a 30-degree angle in between them. Now let's consider what they'll look like if we draw them tip to tail. If we draw them tip to tail, you'll see it looks like what's shown up at the top here. Okay, it'll look like that. And we're going to get an angle between them now that won't be 30 degrees anymore. We need to figure out what that alpha equals. Well, there's a C pattern between those horizontal lines. This polygon, we've created a C pattern here. And we know from earlier grades math that when you have a C pattern with parallel lines, that the two angles inside that C add up to 180 degrees. So in other words, what we're saying is that alpha is 150 degrees. So when we go to add these two vectors, we're going to be using 150 degrees in our calculations. So we put a 150 degree angle there. Now, remember, we're not talking about A plus B, we're talking about 2A plus B. So we're going to maybe redraw the diagram as shown below. And we're going to draw it just a little bit with A drawn twice as long and B still in the same direction, and a 150 degree angle between them. And we're going to try and figure out what would, using the cos law, what would the length of that side of the triangle be, and also we'll eventually figure out what is its direction. Okay? So using the cosine law on the circled triangle there, we see that we get the resultant, which is 2A plus B. That resultant magnitude squared will be 2 squared plus 1 squared minus 2 times 1 times the cos of 150 degrees. And we'll evaluate the cos of 150 degrees, and we'll come up with ultimately that the resultant vector is approximately 2.909 units long. But we also, like we said, need to determine the direction. So we're going to determine the value of the resultant made by determine the angle made by the resultant with one of the vectors in the question drawn tail to tail. And then the tail of that resultant vector will form we'll notice the tail of the resultant vector forms an angle with the vector A. We're going to use the sine law to figure that out. So going back to our question shown right there, we see this new angle that we're now calling alpha, not the same alpha we were describing earlier, but a new angle that we're calling alpha. We're going to try and figure out what is the magnitude of that, because the resultant vector down here is the tail of that is making an angle with another one of the vectors right here, and the angle it's making is this alpha. So going back up to our next slide, we would, if I was to reproduce the earlier slide, it would look something like this. This has a magnitude of 2, this has a magnitude of 1, this has a magnitude of roughly 2.909. We know that this is a 150-degree angle here, and we know that this is what we're calling alpha. Now, to determine the direction, like we said, we're going to use the sine law. Now, you might be tempted to say, well, why don't we use the cosine law here? We can. We can use the cosine law to determine the measure of angle alpha. But we can also use the sine law here. It's safe to do so. And the reason it's safe to do so, meaning we won't get the ambiguous case of the sine law, is because we already know the magnitude of the largest angle. And so since we already know the magnitude of the largest angle, we won't have to worry about not knowing whether the angle that we're looking for now, the alpha, should be acute or obtuse. So using the sine law here, again, just to redraw the triangle, it looked something like this. So using that sine law, we're able to say that the sine of 150 degrees over the magnitude of 2a plus b is going to roughly be equal to the sine of alpha over 1. And we get that right here. And now that would mean that alpha is going to ultimately be roughly equal to 9.9 degrees. So we're going to notice now that there are no indicators in the question giving us direction indicators like north, south, east, west, or left, or right, or clockwise, or counterclockwise. So because of that, we have to state our answer a little bit more abstractly. So what we're going to do, we're going to go back to the original diagram. The original diagram that we drew with the unit vectors looked like this. And then we're going to consider what did the diagram look like when we figured out the resultant. And it looked like that second diagram on the lower left, on the lower right. And then what we're going to do is we're going to say, okay, this alpha that we found was in between the original A and the original B. In this diagram here, it's in between 2A and B. But since the question referred to A and B, we will also refer to A and B. We see that alpha is in between those two, and it's rotated from the A vector towards the B vector. So we're going to be able to say that we have a magnitude of approximately 2.909 in a direction of approximately 9.9 degrees rotated from A towards B. Sometimes to help me do it, what I'll do is after I've done all the difficult work of calculating the correct values, I'll go back to my original diagram, this one on the left, and I'll say, okay, that resultant vector was cutting through the middle here. If I add the 2a, if I make it a 2a and then add the b, that resultant vector was cutting in between them at an angle of 9.9 degrees. And this will help me figure out how do I state this direction using the original A and B. And I can say, okay, I was rotating from the A towards the B, roughly 9.9 degrees. Now, suppose that the magnitude of vector u is 4 and the magnitude of vector v is 5, and suppose further the angle between them is 120 degrees. We want to determine the vector u plus v. So we can draw the original diagram representing what's described in the question right there. Now, moving on, what we're now going to do is we're going to say, okay, what if we are figuring out u plus v? Well, if we're figuring out u plus v, what we have to do is draw u, and then tip to tail draw v, and then we have to figure out what is the magnitude of that angle. Well, going back, like we said earlier, we have a C pattern here, and so we know that these two angles have to add to 180 degrees. So we know that there's going to be a 60 in there because the two vectors are parallel. So we're able to see that our diagram is going to look something like that. Okay. Now, we're going to figure out the magnitude of that third side because if you recall, we know that the magnitude of u is 4, and we know that the magnitude of v is 5, and we know the measure of this angle. So we actually have a side angle side situation, which is perfect for us to use the cosine law. So what we end up being able to say is that the magnitude of that third side, the resultant, the one I just colored in red, we're able to say that that magnitude is root 21. Okay? Now, we also have to be able to say what is the direction of it. So what we're going to do is we're going to figure out what is the angle in between this resultant u plus v. What is the angle made by that resultant vector with one of the other vectors? And in this case, we see we can measure it off with vector u. So we're going to determine what is the measure of that angle alpha, and we're going to use the sine law. And again, you might be a little bit curious, would we not possibly come up with an obtuse angle? And the answer is actually it is possible that that would happen. So using the sine law here is actually a little bit dangerous because what we're doing, and if this is foreign to you, I'll explain it real quick. What we're doing here with that vector v, that's 5 units long, and this vector u is 4 units long, and this vector u plus v is roughly 4.58 units long. It's root 21. Because of that, we know that this is going to have to be the biggest angle because it's opposite the biggest side. Well, we actually don't have to use the sine law here because we have all three side lengths. And because we don't have to use the sine law and we're finding an angle that's going to be the biggest one, it's actually a little bit dangerous for us to be using the cosine law to find out the value of that angle. So we're taking a chance here doing it. It would be smarter at this moment, a little bit of a flaw in this PowerPoint, it would have been smarter for us to set it up as 5 squared equals 4 squared plus root 21 quantity squared minus 2 times 4 times root 21 times cos of alpha. And if you set that up and then solve for alpha, you'll get 70.9 degrees. That is the answer we get using the sine law. But like I said, it would have been a little bit more careful of us to have used the cosine law here. Anyways, regardless, we get an answer of 70.9 degrees here. And we have to state the magnitude and direction. Well, fortunately, we know both. We just have to be a little bit careful about how we're going to do it now, how we're going to describe it. So we're going to take this information right here. Imagine we had both u and v drawn tail to tail, like in the original diagram on the left. We're then going to take u plus v, put it through the middle, just like that. And we're going to say, well, we've already figured out that this is 70.9 degrees approximately. So now we can say exactly what the direction of the vector is. It's going to be approximately 70.9 degrees rotated from u towards v. Similarly, someone else could also say, I think it's 49.1 degrees rotated from v towards u, and that is also correct. So we'll put, like we're saying here, we're going to put u plus v back where it belongs in the original diagram. And when we do that, we see the magnitude is root 21 in a direction 70.9 degrees rotated from u towards v. Now, in this particular picture, we see that we're going to try to come up with descriptions of different sides using vectors given to us in the question. So what we're going to do here is we're going to say, okay, the vector AB is going to be, for us, vector small a. The vector AC for us will be vector small b. And the vector AE for us will be vector small c. Well, if we think about it that way, then to go from C to H is equivalent to taking a journey of vector small c and adding a journey of vector small a. So if you'll notice, traveling down this side is exactly the same direction and same magnitude as traveling down this side. And then traveling across here is the same direction and same magnitude as traveling across here. So it's as if we said C plus A or A plus C. Either one is fine. Okay? Now, similarly, FG, to go from F to G, like this, well, that's like going from F to H, which is like this, and then going H to G, which is like this. Well, going F to H is the same as going A to C, same magnitude, same direction. We know A to C is equal to B. And then going H to G is exactly the opposite as going A to B. If you look at this, A to B goes this way, and H to G goes this way. So since A to B is going to be described as vector small a, I can describe H to G as vector negative a. And so I can say that vector FH plus vector HG is the same as vector B minus vector A. And then finally we get CF. To go from C to F, like that, is to basically go the opposite direction of vector A, and then go the same direction as the opposite direction of vector B, I apologize, and then go the same direction as vector A, and then to go the same direction as vector C. So it's negative B plus A plus C, or what we've described here, A minus B plus C. You could have called that negative B plus A plus C as well. Okay? Now, representing vectors on a Cartesian plane. This is an important skill in this course. We're often going to represent a two-dimensional vector on a Cartesian plane. So a vector that moves 1 unit to the right and 2 units up will be described by the vector 1, 2. A vector moving 3 units to the left and 5 units down will be described by a vector negative 3, negative 5. Because if you go to a Cartesian plane, and you want to go 3 to the left and 5 down, that's like going 3 to the left, 5 down. If you start at the origin, you'd end up at the point negative 3, negative 5. So we call that the vector negative 3, negative 5. And if we had a vector that only moved 10 units down, that would be like moving negative 10 in the y direction, but it didn't move at all, right or left, we would call that 0, negative 10. Now, we often talk about unit vectors on the Cartesian plane. If you recall from earlier in this same video, we said that a unit vector is a vector with a magnitude of 1. So a vector that moves 1 unit to the right is going to be the vector 1, 0, and a vector that moves 1 unit up is going to be the vector 0, 1. Well, those vectors are so significant that they're actually referred to as I and j. So vector I is the vector 1, 0, and vector j is the vector 0, 1. And all vectors represented with components on the two-dimensional Cartesian plane can be described as a sum or difference of those two unit vectors. So for example, the vector 3, negative 4, we could call that 3 times the vector 1, 0 minus 4 times the vector 0, 1. And because 3 times 1, 0 would be like 3, 0, and 4 times 0, 1 would be like 0, 4. And you can actually just subtract the components. 3 minus 0 would be 3, and 0 minus 4 would be negative 4. And so we'll see that you can actually do that with components pretty straightforwardly. Well, we're going to call this 3i minus 4j. So we'll It's important that you know that language when we talk about I and J, what we're talking about in this context. Now, can we use the distributive property with vectors? And the short answer is yes, we can, very conveniently. So suppose we wanted to find out what is 3 times the vector 2a minus 5b plus c minus 2 times the vector a minus 4b plus 6c. It's as easy as it might look. You can simply distribute the 3 into the first bracket and distribute the negative 2 into the second bracket and come up with this expression right here. And then you can collect like terms just like you do with variables. 6a minus 2a is 4a. Negative 15b plus 18b is negative 7b, and 3c minus 12c is negative 9c. And we get our nice answer there. Now, suppose we are told that u is equal to 3, negative 1, and v is equal to 4, negative 7, and w is equal to 10, 1. And we want to know what are the components of the vector 4u plus 2v minus 7w. Well, this is actually fairly easy algebraically once you're used to how to do it. 4u plus 2v minus 7w is just 4 times 3, negative 1, plus 2 times negative 4, negative 7, minus 7 times 10, 1. We're just subbing in for u, v, and w with the question. And then all we do is we distribute the 4 into this bracket, so 4 times 3, negative 1 becomes 12, negative 4. 2 times negative 4, negative 7 becomes negative 8, negative 14. Negative 7 times 10, 1 becomes, with a minus sign in front, it'll become 70, comma 7. So imagine we're just leaving the minus sign there. So we're really only distributing the 7 in. Now, that's what we get here. And now all we have to do is just figure out for our x component, what is 12 plus negative 8 minus 70, or you could have said plus negative 70. So we write 12 minus 8 minus 70. And then here we say what's negative 4 plus negative 14, or in other words, negative 4 minus 14. And then that minus in front, the 7, we get negative 7. And when you add those components up, negative 12 minus 8 minus 70 is negative 66, and negative 4, negative 14 minus 7 is negative 25. And we can write that as negative 66 comma negative 25 with a arrow across the top, or sometimes we don't. You'll notice textbooks sometimes do, sometimes don't, so you need to be prepared if they don't. So sometimes students might say, well, how do we know whether it's if it's just written negative 66, negative 25, how do we know if we're talking about the point or the vector? And the answer is context. The context of the problem will point you in the direction of whether it should be, you're thinking of it as a point or you're thinking of it as a vector. Now, another type of question is the taking different paths question. Okay. One example of a taking different paths question is this. We're given this polygon, the polygon ADHE, and we break the top line into 3 equal lengths, and we break the bottom line into 3 equal lengths as well. Now, what they want to do is have us prove that the vector BF plus the vector CG is equal to the vector AE plus the vector DH. So let's think about what BF plus CG means. BF is this vector right here. So let's imagine for a second we redraw that. I'll do my best redrawing, roughly like that. Now the vector CG looks like this. One goes slightly to the left, the CG goes slightly to the right. So I'll do my best job of estimating what that might look like. I'll say, maybe it looks like that. And so now if I add the BF plus the CG, I get kind of this resultant, which looks almost vertical, I guess. It doesn't have to look vertical for this question to work. It just happens here it does. So basically BF plus CG would kind of roughly be equal to this bolded in vector. Okay. Now let's think about the vector AE. The vector AE goes this way. Well, that kind of goes out a little farther to the left than the other one did. AE goes a little farther out to the left than BF. And then if you look at this DH, it goes a little farther out to the right than this CG did. So if we take that DH, and it's even a little bit longer too. So if we take that DH, make it kind of the longest of the four vectors so far, and then if we draw that resultant, it'll look like this kind of vertical line. And perhaps I haven't done the best job. But what we're trying to show here is that this vertical line here, that resultant, should actually perfectly equal that vertical line there. Now, obviously, it's not good enough just to draw them like this and say close enough. So we're going to take what I call a different paths approach to this. So what we're going to do, instead of going from B straight to F, the way we could, a sensible way of doing it, we're going to take the scenic route. We're going to go from B to A, and then we're going to go from A to E, and then we're going to go from E to F. Okay? All right. Now, instead of going from C to G and just going straight there like a sensible person might, we could do the scenic route, go from C to D, from D to H, and H to G. Okay? So by the same token, we would say that going from C to G would be the same as going C to D plus D to H plus H to G. So hopefully by now you're starting to see how we're adding these vectors, and hopefully it makes sense to you that we're saying BF is the same as BA plus AE plus EF, and CG is the same as CD plus DH plus HG. Now, what we're going to do is we're going to add them up. On the left-hand side, we've got BF plus CG. And so when we add them up on the left-hand side, we'll just simply get BF plus CG. I should put my vector symbols here. There we go. We should get BF plus CG. On the right-hand side, though, we're going to get BA plus CD. We're going to put that in a bracket. And then we're going to get AE plus DH. We're going to put that in a bracket. And then we're going to get EF plus HG, and we can put that in a bracket if we want. And now, just think about this for a second. Look at this BA plus CD. BA goes this way. CD goes in exactly the opposite direction, and we know they're the same length. So if I go from B to A, and then I go from C to D, I've literally gotten back to the starting point. I've done the zero vector there. Now, AE plus DH remains AE plus DH. Okay, so BA plus CD is the zero vector. AE plus DH is AE plus DH. Now let's look at EF plus HG. EF goes this way. HG goes in exactly the opposite direction, the same length, because they have these triple slashes here. So we can see that EF plus HG will equal 0 as well. So if I take this 0 plus AE plus DH and add 0, what I end up with is AE plus DH. And I've literally proven the thing they wanted me to prove. BF plus CG equals AE plus DH. So we'll show it a little more nicely here. So we're going to add the columns. So BA and CD are opposite vectors. BA and CD are opposite vectors, and as we discussed earlier, same magnitude, opposite direction. They're going to add to 0. And EF and HG are opposite vectors, so when we take EF and add it, when we take this EF and add it to HG, they're the same magnitude, opposite directions. They're going to add to 0. And now the middle column will just stay as AE plus DH, so we can put it there. And what we've actually just shown, if you really look at it, is that BF plus CG ultimately equals AE plus DH. Pretty cool proof. And now one more example. We're going to be given that the vector AD is equal to 3/5 of the vector BC. Now, we're saying that it's equal to 3/5 of the magnitude, but we're also saying that they're in the exact same direction. They're parallel. And that's going to become important later. They want us to prove that AE, which is this vector right here, is going to be equal to 5/8 of AD and 3/8 of AB. So if we took 3/8 of that and added it to that, we would ultimately get that. Okay, so that's kind of might look like a tough question. So let's take a very logical approach to it. Since AD is equal to 3/5 of BC, we know that the top side length and the bottom side length are parallel. So I'm going to put those little parallel lines there. Now, if we use Z patterns, that means where those two red check marks are, I know that those angles have to be equal to each other. And again, using Z patterns, if you look where those two X's are, those two angles have to be equal to each other. So let's go back one just for a sec in case that didn't make sense. Think about what you learned in previous grades about Z patterns. If I know the top and bottom lines are parallel, then that means that angle and that angle must be equal to each other. And similarly, if I know the top and bottom lines are parallel, then using a different Z pattern, I see that those two angles must be equal to each other. And just using the opposite angle theorem, in other words, you make an X and the two angles opposite have to be equal to each other, we see that those two angles are equal to each other. And so now if you look at the top, what we've really got here, we've got ADE, and then in the bottom, we've got BEC, and both of them have the exact same three angles. So probably in about grade 10, you would have learned about similar triangles. What that means is the side lengths have to be proportional. So if you take this side length, which is the side length between the X and the check mark, and you figure out its proportion to this side length, which is the side length between the bottom one's X and the check mark, then whatever that ratio equals, and we know it to be 3/5, that must be the same as the ratio between other corresponding side lengths. So specifically, look at this top triangle where I'm drawing this squiggly line. That's the side length between the X and the theta symbol. Well, that side length must therefore be equal to 3/5 of this side length, which is the side length between the bottom triangles, X and the theta symbol. And then if I look at one more, I'll draw another one, I'll make it bold. If you look at this bold line on the bottom triangle, that's between the check mark and the theta. Well, it must be equal to 5/3 in this case, the reciprocal, or a better way of saying it, this bottom one here, sorry, this top one where the side length that I'm pointing at, that is between the check mark and the theta of the top triangle, and it must be equal to 3/5 of the side length of the on the triangle on the bottom of the side length between the check mark and the theta symbol. So we'll make it look a little bit neater. That might have made sense, might not have, but um, give it a shot as we keep on going. We'll sort of try our best to re-explain it. So like it says here, notice that triangle ADE and triangle CBE have the same three angles. I'm now repeating myself. Now this means they're similar triangles. Now we know that AD is 3/5 as long as BC. So that means if AD is 3 green units long, then BC will be 5 green units long. Now I'm going to ask you to just use your imagination here. Just imagine that those, I know it's drawn roughly with my hand, but just imagine that those 8 green units you see on your screen, they're all exactly the same length. The top is 3 green units long, the bottom is 5 green units long. Now, the side lengths between the X and the check mark on the top versus the bottom are in a 3:5 ratio. So therefore, the side lengths between the X and the theta, this one and this one, they must also be in a 3:5 ratio. But this side length isn't necessarily equal to this side length. So I can't say 3 green units and 5 green units like I did a minute ago because those concepts are already taken. So this might sound a little funny, but we're just going to call them orange units. Look at this top one because we said a minute ago this side length and this side length must be in a 3:5 ratio. So I'm saying they are in a 3:5 ratio. One is 3 orange units long, one is 5 orange units long. Now, similarly, this side length must be in a 3:5 ratio with that side length. Well, we've used green and orange. Why don't we use blue? The top one will be 3 green units long. The bottom one will be 3 blue units long. The bottom one will be 5 blue units long. Now, we're going to try to write an equation directionally consistent with the equation we're trying to prove. So here's what I mean by that. AE, I have to somehow write an equation where the left-hand side, AE, like AE goes in this direction. And that's the left-hand side of the equation I'm trying to prove. Well, the only other vector I can think of that goes in the same direction is AC. So I'm going to write an equation that starts with AC. Okay, this will be the beginning of my proof. Now I look at this 5/8 of AD. Well, I know 5/8 of AD goes in this direction along the top. So obviously so does 5/8 of AD. So I'll put an AD here. And I know AB, here's AB. Oh, sorry, here's AB here. Well, AB goes in this direction, so does 3/8 of AB. So what I'm going to do, I'm going to say, oh, sorry, give me one more shot at this. Let me just scale back for a second. What I said at the start is correct. This AE is directionally consistent with this AC. They both go in identical directions. So let's look at this. This 5/8 of AD goes in the direction shown along the top. So does the vector BC. They go in exactly the same direction. So I'm going to put BC here. So this 5/8 AD goes in the same direction as AD, which goes in the same direction as BC. And then this 3/8 of AB right here, that goes in the same direction as AB, obviously. And so what I've done now takes a little bit of artisticness to do it, but I've made a statement on the bottom, AC equals AB plus BC. If you just look at that statement, if you just look at that statement on its own, it's kind of obvious. Yeah, I agree. AC equals AB plus BC. And you might be saying, well, what's the point of that? How's that helpful to me? Here's how. It's directionally consistent with that thing I'm trying to prove. Specifically, AE is in the same direction as AC, 5/8 AD is in the same direction as BC, and 3/8 AB is in the same direction as AB. So I've made a starting point that I can now that I've got my directions in line, I can now start working with my quantities with all those ratios that we talked about earlier. So that's what this says. AC equals AB plus BC. Right there. There's the first line of our proof, so to speak. And one more time, AE is diagonally here. AC is diagonally here. So this AE is directionally consistent with this AC. Then 5/8 AD is in the same direction as AD, which is in the same direction as BC. So that's directionally consistent. And this 3/8 AB is in the same direction as AB. So those two right here, they're directionally consistent. So I've made a good first line for my proof. Now, it says here AC is parallel to AE, AB is parallel to 3/8 of AB, BC is parallel to 5/8 of AD. Okay, so there we go. We begin our solution. Now, we know that AC, which is this whole long thing here, that is 8 orange units long, and AE is 3 orange units long. AE is in the same direction, but it's only 3/8 as long. So we can simply take this AC and multiply it by 3/8 to get AE. So we're going to multiply AC by 3/8 to get AE. In other words, this is AC, 8 units long. This is AE, 3 units long. Multiply this AC by 3/8 and you'll have AE. So because it's an equation, we have to multiply everything by 3/8. And so that's what we do. Starting with this thing that I've now totally over-explained, we multiply both sides by that 3/8. We re-express 3/8 AC as AE because if that's 8 units long and that's 3 units long, it's 3/8 of it. And now we have 3/8 of AB plus 3/8 of BC. Well, we're just going to simply switch these direct. We're going to just switch those two. So we'll call it 3/8 of BC plus 3/8 of AB. Now, we're getting close. We're getting pretty close because what we're asked to prove has an AE on the left and has a 3/8 of AB on the last term. We just have to somehow show that 5/8 of AD is the same as 3/8 of BC. How are we going to do that? Well, let's think about the relationship between BC and AD. Let's think about the relationship between BC and AD. The question tells us that AD is 5/3 of BC. It's right in the question. So that means BC must be 5/3 of AD. If AD is 3/5 of BC, then BC is 5/3 of AD. Literally divide both sides by 3/5, or another way of saying that is multiply both sides by 5/3. Okay? So instead of saying what we have here, 3/8 of BC plus 3/8 of AB, let's call it 3/8 of 5/3 of AD. BC is equal to 5/3 of AD from that statement right there. And then multiplying 3/8 times 5/3, you get 15 over 24, which is 5/8. And we get the thing that we were asked to prove, that AE is equal to 5/8 AD plus 3/8 AB. There you go. And we get a smiley face because we definitely earned it.